Character evaluations are closely related to a problem in graph coloring. Maybe that's not too surprising given the Littlewood-Maris-Watkins generating function, which is a sum of products of minors, which made us think of different path families in a graph where the path families were colored different colors and no two paths of the same color could intersect. So given a graph which is undirected, G, Stanley defined capital X sub G, called the chromatic symmetric function, of G to be equal to, we can define it, its expansion on the monomial basis by this coefficient A lambda is the number of ways to properly color G so that is that no adjacent vertices can have the same color. So the number of ways to properly color G with lambda I vertices of color 1 lambda 2 vertices of color 2, etc. Now since xg is symmetric, well, first let me say, so this is defined to be in the non-negative span of the monomial symmetric functions. And if it's an n-vertex graph. Now we can expand xg in other bases. And ask if it is E positive or S positive. This is a weaker statement to say that it's sure positive, because every elementary symmetric function is a non-negative linear combination of sure functions. So if it's E positive, then it's definitely sure positive. Now, alright, so what I was saying before is that it's a symmetric function. So that means that the coefficient of m lambda is an induced sign character evaluated at something. So some element little g that depends on the graph capital G in the symmetric group algebra with rational coefficients. So that means that this chromatic symmetric function is for some element little g, we can write it as induced sign character evaluated at g, sum over all those indexed by lambda, or irreducible character evaluated at g times a Schur function, sum of those over all lambda. Or monomial trace evaluated at g, e lambda, etc. So asking if it is Schur positive is equivalent to asking if all irreducible characters at this evaluated at this element g, whatever it is, are non-negative integers. Asking if it is elementary positive is equivalent to asking if all of these monomial traces are non-negative, all those evaluations for all lambda. And no characterization of the graphs G or elements G in the symmetric group algebra. That make this Schur positive or elementary positive. Are known, but there are some partial results and conjectures. And some of them involve posets. So for any poset P, define the graph INC of P, called the incomparability graph. Of P to be the graph that has the elements of P as vertices and an edge for every pair of vertices that are not comparable. So for example, if P is this poset, then the incomparability graph of P is 2 is incomparable to 1 and 3 and 4. 1, 3, and 4 are all incomparable to each other. 1 is less than 1, 3, and 4 are all comparable to each other. 1 is less than 3, 3 is less than 4. So this is the incomparability graph. Let's look at some more examples. So if P is 1, let's say this is a graph we looked at in another, a poset we looked at in another example. So 3 is incomparable to everything. 1 is less than 4 and 5. 2 is less than only 5. So the incomparability graph is, well, 3 is incomparable to everything. One is incomparable to 2. 2 is incomparable to 4. 4 is incomparable to 5. So we get this graph here. And of course, when P is a chain or an anti-chain, we get interesting special cases. So if P is a chain, then the incomparability graph is, well, everything here is comparable. One element is less than another, etc. So the incomparability graph has no edges, however many elements there are. And then when P is an anti-chain, so no comparabilities here at all. If nothing's comparable, then that means that everything is connected in the incomparability graph. Now Stanley and Stembridge conjectured that if P is 3 plus 1 free, then the chromatic symmetric function of the incomparability graph of P is E positive. A weaker version of this conjecture is that it's sure positive. Let's take a closer look at the chromatic symmetric function of the incomparability graphs of posets. The vertices in the incomparability graph can be colored the same if they're non-adjacent. The adjacent vertices in the incomparability graph are the ones that are incomparable to poset. The non-adjacent vertices in the graph, so these are elements that are comparable in P. That is, they're chains in P. So coloring, now mutually non-adjacent elements of vertices in a graph are called independent sets. So coloring independent sets, or coloring an independent set by one color. In the incomparability graph is the same as coloring a chain by one color in P. So giving different independent sets different colors is like giving different chains in the post set different colors. So we're coloring the graph so that every single color corresponds to an independent set. We're coloring a post set so that every single color corresponds to a chain. So if we write this definition again, these coefficients A lambda can be interpreted in terms of coloring chains. So A lambda is the number of ways to color elements of P so that some lambda 1 element chain has color 1 and some lambda 2 element chain has color 2, etc. So that's sort of like making a column strict P tableau. In fact, it's exactly column strict P tableau. Number of column strict P tableau of shape lambda transpose, because there'll be lambda 1 elements in column 1 corresponding to one color, lambda 2 transpose, lambda 2 elements in column 2 getting another color. Now if P is the unit interval order, corresponding to some 3, 1, 2 avoiding permutation W and Sn, then A lambda is precisely epsilon lambda of the Kajstanolistic basis element CW. So that means that CW in the group algebra is precisely the element G corresponding to the graph capital G equals incomparability graph of P. So this is the element that we're taking trace evaluations of and putting next to the different symmetric functions. thus for P a unit interval order, the chromatic symmetric function being E positive corresponds to all of the monomial trace evaluations at this one Cauchy-Johnson basis element being non-negative for all lambda. And saying that it's sure positive is equivalent to all of the irreducible character evaluations being non-negative. Now these are special cases of the 3+1 free poset conjecture. There are special cases of the 3+1 free poset conjecture because unit interval orders which avoid 3+1 and 2+2 are a subset of the 3+1 free posets. At least that was the way it looked at first. But actually, Gay-Paquet proved that for any 3+1 free poset, let's say Q, we have the chromatic symmetric function indexed by Q belongs to the positive rational span of chromatic symmetric functions indexed by unit interval orders. So therefore, proving the positivity results, I should call them statements, they're not results yet. So proving positivity statements for all unit interval orders is equivalent to proving the statements for all 3+1 free posets. Now Gosharov came up with the first result in this direction. That is, that if P is 3+1 free, then the chromatic symmetric function for the incomparability of graph of P is sure positive. Furthermore, the coefficient of S lambda is equal to the number of standard P tableau of shape lambda transpose. So by standard I mean column strict and row semi-strict. So weakly increasing in rows and strictly increasing in columns. So equivalently, if W avoids 312, or we could say 3412 and 4231, because the corresponding poset, the path poset of FW would be the same either way. Then chi lambda of the Kaj-Johnlistic basis element CW equals the number of standard PFW tableau of shape lambda. So recall we don't need a transpose here because it's already counted for there. So next to the sure function S lambda, we have the evaluation of the irreducible character indexed by lambda transpose. So let's do an example of this. Let's use the same example we used for induced trivial characters. Let's look at W equals 1342. So the poset is one is less than 2 is less than 4. 3 is incomparable to all of them except for it's greater than 1. And let's use lambda 31 and compute chi 31 of C1342. So we just have to draw all the standard, that is column strict and row semi-strict, P tableau of shape 3-1. So in the first column we need to pick two elements that are comparable, say 1 and 2. And then the other ones can go in any order as long as we don't put one element and then follow it by an element that's less than it in the poset. So 3 and 4 are incomparable, so there's no danger of that here. 1, 2, 3, 4, 1, 2, 4, 3 are both good. And then if we have 1 and 3 in the first column, we can have 2 and 4 after that, but not 4 and 2, because 4 is greater than 2 in the poset, so it's not allowed to come first in a row. Then let's see, what are the other possibilities. 1, 4 could go in the first column, and then 2 and 3 are incomparable, so they could go in either order after the 1. 2 and 4 is another chain, but then we're stuck. 1 is less than 3, but 2 is greater than 1. So this column, this row would not be row semi-strict, so that's not allowed. And I think we've exhausted all of the different 2-element chains that could be in the first column, so that's got to be it. So thus we have chi3 1 of C1342 equals 1, 2, 3, 4, 5. The end.